Hello everyone, I'm Amodini. I'm a student at IIIT Sri City. I'm pursuing my BTech in computer science, and today I'll be covering PYQs on the topic dual nature of radiation and matter. Okay, so the first question is, electrons used in an electron microscope are accelerated by a voltage of 25 kilovolt. If the voltage is increased to 100 kilovolt, then the de Broglie wavelength associated with the electrons would be. Okay, so they are telling that the voltage initially was 25 kilovolt, right? If the voltage is increased to 100, so later let's call this V dash, it has been increased to 100 kilovolt, right? Yeah. So we are supposed to calculate the de Broglie wavelength. We know that lambda, that is our de Broglie wavelength, is inversely proportional to the root of voltage, right? So I can write that lambda 1 by lambda 2 will be equal to, this is V1 and this is V2, okay? Will be equal to whole root of V2 by V1, right? So with that, I can tell that it's going to be 100 by 25, and that is nothing but 4. And root of 4 is equal to 2. So we can say that the lambda decreases by 2 times. It's not increases because it is lambda 1 by lambda 2, right? So it decreases by 2 times. So our option B is the correct answer, right? Let's move on to the next question. Light of frequency 1.5 times the threshold frequency is incident on a photosensitive material. What will be the photoelectric current if the frequency is halved and the intensity is doubled? Okay, so this is a different question than the before one. So what they are telling is, for a photoelectric emission, okay, there is a photoelectric emission, right? Yeah. There's a photoelectric emission. And when we talk about photoelectric emission, we know that the light of frequency is 1.5 times the threshold frequency. Okay, so we can tell that our V, let's do it this way, is equal to 3 by 2 of V naught. Yes, 3 by 2 is nothing but 1.5, right? So if the frequency is halved, okay, so that means our V dash would be V by 2, right? Let's call it V dash, okay? Would be V by 2. And that is nothing but 3 by 4 of initial threshold frequency, right? So no photoelectric emission will take place because V dash is less than V naught. And we know that for a photoelectric emission to take place, our V dash should be greater than the threshold frequency, right? So that will be our option C, 0, because the photoelectric current wouldn't even pass, right? Yeah. Let's move on to the next question. Einstein work on the photoelectric effect provided support for the equation what? So we all know that the Einstein work on photoelectric supports the equation E is equal to Planck constant into the frequency, right? It is based on the quantum theory of light. Right? So that is E is equal to H. Right. Okay, let's move on to the next question. A particle of mass 1 milligram has the same wavelength as an electron moving with a velocity of 3 into 10 to the power 6 meter per second. The velocity of the particle is what? So we have been given mass equal to 1 mg, and we have been given the velocity, and velocity is equal to 3 into 10 to the power of 6 meter per second, right? So I can tell that my lambda 1 is equal to h by mv. Yes, we can tell that. And that will be equal to h by, we don't know the velocity. So it'll be like, m is nothing but the mass of the electron, right? So 9.1 into 10 to the power minus 31 into 3 into 10 to the power of 6. Right? This is the thing. We know this. And we know that lambda 2, that is, it has been given. The particle's mass is 1 into 10 to the power of minus 6, right? In kg, we are bringing this to the kg one, right? Because it is already 1 into 10 to the power of minus 3 gram. And if I still further convert it into 10 to the kg, it will be 10 to the power minus 6 kg, right? And this is also in kg. So we are bringing it all to the same units, right? So we know that lambda 1 is equal to lambda 2. It has been given, right? It has the same wavelength. It has been given. So therefore, we equate lambda 1 is equal to lambda 2 and further find the answer. So with this, we can cancel out h and h, and then further we can calculate the velocity of the particle, and that turns out to be 2.73 into 10 to the power minus 18, and that is our option A. Okay, let's move on to the next question. In a discharge tube, ionization of enclosed gas is produced due to collisions between negative electrons in neutral atoms or molecules, photons in neutral atoms or molecules, neutral gas atoms or molecules, neutral gas atoms, positive ions, and neutral atoms or molecules. Okay, so we know that it is produced by A. And how do we know that? When electrons emitted from the cathode. Okay, let's call this a cathode tube. Okay, so when the electrons are emitted over here, okay, it's emitted from the cathode, they collide with the gas molecules or atoms, they knock out. Okay, so there are gas molecules also. So they collide over here and they knock out other electrons and produce positively charged ions, right? So they produce positively charged ions. Okay. So therefore, it brings up the positive rays, right? And therefore, we can tell that the negative electrons and the neutral atoms or molecules collision will produce the ionization of enclosed gas, right? Because positively charged ions are produced. Okay, the next question. Which of the following particles has largest wavelength of matter waves? Electron, alpha particle, proton, neutron. And we know that the correct answer is electron. How do we know that? We know that de Broglie wavelength, okay, is equal to h by mv. Yes, this is nothing but de Broglie wavelength. Right? And we know that for same velocity, lambda would be inversely proportional to the mass, right? And out of all these, we know that electron has the least mass, right? So therefore, we can tell that since it's inversely proportional, that means the de Broglie wavelength is the maximum, right? This is less, that means this increases. Therefore, our electron is the one that has the largest wavelength of matter waves. Okay, let's move on to the next question. Which of the following statements is not true for cathode rays? Okay, so cathode rays produce heat when incident on metals. Cathode rays travel in a straight line. Cathode rays do not deflect in electric field. Cathode rays produce fluorescence when they fall on certain materials. And the correct option is C. We know that cathode rays are what? Negatively charged rays, right? We know that. And hence, when electric field is applied to them, then they deflect in direction opposite to the electric field. So therefore, since there's an electron over here, let's say, okay, this is negatively charged basically. So when you put an electric field in this direction, then they start deflecting, okay? They start moving somewhere else. They start deflecting in the opposite direction. They were moving in this direction. On applying the electric field, they start moving in this direction, okay? Yeah. So moving on to the next question. The wavelength associated with an electron accelerated through a potential difference of 100 volt is of the order of 1000 angstrom, 100 angstrom, 10.5, 1.2. Okay, so first of all, we have been given the potential difference, that is big V is equal to 100 volts. Okay, and we have been given that we know that kinetic energy acquired by any electron would be, let's call it Ke, will be equal to 100 into E, right? Yeah. So I can tell that my half mv square is equal to 100 times E. Yes, E is the charge, right? So I can tell that my V is equal to root of 2E into 100 divided by M. Yes, and we know by the de Broglie's concept that lambda is equal to h, that is our Planck's constant, divided by mv. So I can substitute my v value here. So on substituting, I'll get something like this, and it's going to be h by root of 2m E into 100. Why is there M? Because M was outside and this was here. It gets cancelled out. So basically, I can write this over here as root M. So when you like cancel it out, you're left with root M over here, right? So that's why we get this, okay? And after substituting the values, we get it to be 1.2 into 10 to the power minus 10, right? This is in meter. And we know that in angstrom, it's nothing but 1.2 angstrom. And that is our option D. Yes. We could have, substituted, we'll be substituting the values of M, mass of the electron, that is nothing but 9.1 into 10 to the power minus 31 kg. And E is the electric charge, and that's nothing but 1.6 into 10 to the power of minus 19 coulomb, and H, our Planck's constant, is nothing but 6.63 into 10 to the power of minus 34 joules second, right? Okay, let's move on to the next question. Gases begin to conduct electricity at low pressure because at low pressure, gases turn off plasma. Colliding electrons can acquire high kinetic energy due to increased mean free path, leading to ionization of atoms. Atoms break up into electrons and protons. The electrons in atoms can move freely at low pressures. The, the correct option is option B. Okay, and why is that? We know that ionization, okay? Ionization requires high energy electrons. We know that, okay? Let's move on to the next question. An electron is accelerated through a potential difference of 10,000 volt. Its de Broglie wavelength is nearly what? Okay, so we have been given that lambda is equal to what we need to calculate, and we know voltage is equal to 10,000 volts, and we know the mass of electron. And we previously just calculated how this one, right? We know that it is h by root of 2 MeV, right? I can further, I can actually calculate this part and remember it as one of the formula. And I'll let you guys know what the formula is, okay? So this part, we can calculate it beforehand only. So by calculating it beforehand, you'll get it like 12.27 divided by root of V angstrom, right? So I can tell that it's nothing but 12.27 divided by 10,000, right? This is equal to my lambda. And with this, I'll get my lambda to be 12.27 into 10 to the power of minus 12 meter. We get it 10 to the power of minus 2, but since we need to find it out in meter, and we know that 1 angstrom is equal to 10 to the power minus 10 meter, we'll be substituting it, and with this, we'll get our option B to be the right answer. Okay, moving on to the next question. An ionization chamber with parallel conducting plates as anode and cathode has 5 into 10 to the power 7 electrons and the same number of singly charged positive ions per centimeter cube. The electrons are moving towards the anode with 0.4 meter per second. The current density from anode to cathode is 4 mu ampere per meter square. The velocity of positive ions moving towards cathode is. Okay, so we have been given that there are like two parallel plates, okay? Yeah, there are two parallel plates. One is anode and one is cathode. Right? So I can tell that what they are telling is cathode has 5 into 10 to the power 7 electrons. So there are 5 into 10 to the power 7 electrons and the same number of singly positively charged. Okay, so the electrons are moving towards the ion node. So it's moving in this direction. Okay, and the velocity is 0.4 meter per second. This is the electron's velocity. And we need to calculate the positive ions velocity, right? So we can tell that the current is equal to the current produced by electrons plus the positively charged ions. Okay, so it's, yeah, So we know that I is equal to NEAVD, and here N is our 5 into 10 to the power 7 per centimeter cube. But then we need to bring it to meter cube. So I can tell that it is nothing but 5 into 10 to the power 13 per meter cube. Yes, I can bring it to this. And we know that IE. Okay, let's calculate IE. It is NEAVD, and we know that it is nothing but 5 into 10 to the power 13 into E is nothing but 1.6 into 10 to the power minus 19. And we also know that A is, yeah, let's make some space. We know that we'll just keep A as the same because the area is going to be the same one. So we don't need to calculate it twice, right? Okay. So I can write that into A, and we know the potential difference or the current density to be 0.4 velocity. Okay. So I can write similarly IP. IP is nothing but for the positively charged ion. So I can write this as 5 into 10 to the power 13 into positively charged ions has the same, but then the sign differs. So it's again 1.6 into 10 to the power minus 19 into A, but we don't know the velocity. We're supposed to calculate the velocity, right? So now what we'll do is we'll put these values in the first equation, and with that we'll be getting this. Okay, so we can further write, we have been given that current per area, that's the density, it has been given to be 4 into 10 to the power minus 16 ampere per 6 ampere per meter square. Yes, it has been given over here, right? So we have been given this. So what we'll do is we'll just substitute it. Substituting the values over here, you'll get finally that our velocity is 0.1 meter per second. Yes, we just substitute the values directly. We equate these and then substitute it, and then finally you get it to be 0.1 meter per second, and that is our option D. Okay. Yeah. Moving on to the next question. The work function of a photosensitive material is 4.0 voltage. Okay. And then the longest wavelength of light can cause photon emission from the substance is. So we are supposed to calculate the longest wavelength basically. And we know that this is also one of the formula that we have to remember. And that is E is equal to 12,400 divided by lambda. And that is nothing but lambda would give you, it is 4, right? Here we have been given it's 4. So 12400 divided by 4, and that is 3100 angstrom. Remember that these things are in angstrom. So I can further write this as 310 nanometer. Right? We know the 1 angstrom is equal to 10 to the power minus 10 meter, and 1 nanometer is equal to 10 to the power minus 9 meter. So with that relation, you'll get 310, and that is our option A. Here again, it was quite a tricky move. If we wouldn't remember that here we'll be using angstrom, so there was a high possibility that we could have chosen the option B to be the correct one. So therefore, units are extremely important. Okay, moving on to the next question. The photoelectric threshold wavelength of silver is 3250 into 10 to the power minus 10 meter. The velocity of the electron ejected from a silver surface by ultraviolet light of wavelength 2536 into 10 to the power minus 10 meter is. So we have been given the Planck's constant, the charge and everything, the velocity, right? So we're supposed to calculate the velocity. So that would be, first of all, we have been given threshold, that is lambda naught, and that is 3250 into 10 to the power of minus 10 meter, right? And we have been given lambda, and that is 2536 into 10 to the power minus 10 meter. Yeah. So we know that phi would be equal to hc by lambda naught, right? So I can substitute the values over here. We have been given the value of h, and that is 4.14. You can see that there is a change in the values, like units, into 10 to the power minus 15 into 3 into 10 to the power 8 divided by lambda naught is 3250 into 10 to the power minus 10. Okay. So with this, you'll get the phi to be 3.82 EV, right? And similarly, we know that HV is equal to HC by lambda, right? I can cancel out the H here. So I can tell that my HV is nothing but 4.89 EV. Yes, we got two values, and we know the Einstein's photoelectric equation, and that is nothing but K max is equal to HV minus phi, right? And we know that here KE max is equal to 4.89 minus 3.82, and you'll get it as 1.077 EV. But we are supposed to find out the velocity. So therefore, I can just calculate it using half mv square. We know the mass, we know the charge and everything. So I can write this basically as 1.077, and E is nothing but 1.6 into 10 to the power minus 19, right? We know the mass to be 9.1 into 10 to the power minus 31. With this, we'll get our velocity to be 0.6 into 10 to the power 6 meter per second, or 6 into 10 to the power 5 meter per second. And that is our option A and as well as D. It's nothing but, it's just a tricky part, right? We just move the units here and there, and then you get both the answers. So therefore, it has two correct answers here. Moving on to the next question. When a metallic surface is illuminated with radiation of wavelength lambda, the stopping potential is V. If the same surface is illuminated with the radiation of wavelength 2 lambda, the stopping potential is V by 4. The threshold wavelength for the metallic surface is, okay, so here we know that EV is equal to hc by lambda minus hc by lambda naught. This is the threshold one, right? And we also can also tell that since it drops to V by 4, EV by 4 is equal to hc by, since the wavelength has been increased to 2 lambda, right? hc 2 lambda minus the threshold again, hc by lambda naught, right? So I can divide these both equations. This is equation 1 and this is equation 2. Dividing these equation, I can tell that 4 is equal to, it is nothing but 1 by lambda minus 1 by lambda naught divided by 1 by 2 lambda minus 1 by lambda naught, right? So with this equation, I can tell that my lambda naught is equal to 3 lambda. Okay. And since the threshold wavelength is the maximum wavelength of the incident radiation required to eject the electrons from the metallic surface, we can see that our initially it was lambda and 2 lambda. And both the times it was lesser than lambda naught, right? So therefore, no photoelectric emission took place, and the threshold wavelength is 3 lambda, right? Okay, moving on to the next question. A certain metallic surface is illuminated with monochromatic light of wavelength lambda. The stopping potential for photoelectric current for this light is 3 V naught. If the same surface is illuminated with a light of wavelength 2 lambda, the stopping potential is V naught. The threshold wavelength, again, this is the similar one. So again, I'll write this as EV is equal to HC by lambda minus pi. Okay. And similarly, I'll write this again as it becomes 3 EV naught, right? Is equal to HC lambda by minus again pi. And I can tell that this is the equation, right? This is one of the equation. This is the first one. And then we know that it becomes EV naught, but it is HC by 2 lambda minus phi 2. And then it becomes 3 EV naught divided by, sorry, and that is equal to, from these two equations, I can tell that it is nothing but 3 HC by 2 lambda minus 3 phi. So what did I just do? I just add these up and then you get this to be our answer. So multiplying equation 2 by 3 and subtracting it from equation. So I multiply, this is my equation 3, right? So I multiply these two and then subtract it from equation 1. So with this, I'll get that my phi is nothing but HC by 4 lambda. Okay. So with this, I can tell that my lambda threshold is nothing but I bring it here and then this goes down here. So I can write it to be HC by phi. And we know that phi is equal to HC by 4 lambda again. Again, I'll write this to be HC by 4 lambda. And cancelling this, you get it to be 4 lambda. And that is your option A. Okay. Moving on to the next question. Light of wavelength 500 nanometer is incident on a metal with work function 2.28 eV. The wavelength of the emitted electron is, okay, so work function has been given to be phi is equal to 2.28 eV. Okay. We know that lambda is 500 nanometer. Yes. We also know that we can just write this as 500 into 10 to the power minus 9 meter. Yes. Okay. So I can write my KE max to be HC by lambda minus phi. We know the values over here. H is 6.6 into 10 to the power minus 34 and C is 3 into 10 to the power 8 and lambda over here is nothing but 1 is 500 into 10 to the power minus 9. Okay. So I can write this further as my KE max to be like substituting the values, you'll get it to be 0.2 EV, right? But then what do we need? We are supposed to calculate the minimum wavelength because it's the wavelength emitted, right? And that I can calculate by h by p. And p is nothing but p is equal to root 2 m ke max, right? We know that. So substituting all the values, you get your option B to be the right answer. And why do we select it to be greater than that? Because we have to have it greater than that since photoelectric emission has to happen. Okay, moving on to the next question. A photoelectric surface is illuminated successively by monochromatic light of wavelength lambda and lambda by 2. If the maximum kinetic energy of the emitted electrons in the second case is 3 times that the first case, the work function of the surface material is. So it has been given that we'll be using directly HC. Okay, so I can tell that first EK1, okay? This was going to be maximum. So that is equal to HC by lambda minus 5. Yes. And I can tell that similarly EK2. It has been given that it becomes lambda by 2. So I can write this as 2HC by lambda and it is again minus 5. Right? So from equation 1 and 2, you'll get it as EK2 is equal to 3 EK1, right? So I can write this further as 3 EK1 or KE1 is equal to 3 into HC by lambda minus 5, right? This was the first equation. So from I can again use these 2 and 3 equation to get that my work function is nothing but HC by 2 lambda. And that is my option D. Yes? Okay. Moving on to the next question. When the energy of the incident radiation is increased by 20%, the kinetic energy of the photoelectrons emitted from a surface increased from 0.5 eV to 0.8 eV. The work function of the metal is, okay, so we know the Einstein's photoelectric equation, that is nothing but HV is equal to phi naught plus K max, right? So I can tell that first it was HV, my HV was equal to phi naught plus it was 0.5 and then it became 0.8, right? And they're telling it increased by 20%. So I can tell that it is nothing but 1.2 HV. How? It was 1 and then you add 20% to it. 20% of it is nothing but 0.2. So you add it, so it's going to be 1.2, right? Is equal to phi naught plus 0.8. You've got two equations, 1 and 2. So using these two equations, I can drop it down to the fact that phi naught is equal to 1.0 EV. So the work function varies from metal to metal, okay? So the material is better for photoelectric emission whose work function is least. And cesium has the least work function. So therefore it has the best metal photoelectric emission and therefore our answer is option B and this is the correct one. Okay. So we covered different kinds of questions today. Okay. So we'll be revising a bit of concepts of dual radiation. Okay. So firstly, let's talk about what exactly do you mean by dual nature of matter. So when we talk about dual nature of matter, dual nature of matter. Right. So when we talk about this, it's basically that it states that a matter exhibits both particle nature and wave nature. It exhibits particle nature and wave nature. Okay. So it means that when a matter is at rest, it behaves like a particle, and when it is moving, it behaves like a wave, right? So different experiments have been performed to be proven. Okay. So what are the important concepts when it comes to dual nature? Okay, so we'll talk about those. So few of the important concepts are electronic emission, right? Electronic emission. And then there's photoelectric effect, right? We all will know about photoelectric effect. Okay. So we also know about particle nature of light, and then we also know about Davidson German experiment and all these. So first let's talk about electronic emission. So electronic emission refers to the ejection of an electron. Okay, it's nothing but ejection of an electron, okay, from a matter, basically from the surface of matter. So this phenomenon can be stimulated by various factors such as temperature elevation, radiation, or any such factors. Okay, so there are different types of electronic emission. There is thermionic, photoelectric, and field emission. So basically we'll be concentrating more on photoelectric effect. Okay, so, photoelectric effect is the phenomenon in which electrons are ejected from the surfaces of a material when it absorbs electromagnetic electromagnetic radiation, okay, such as light, basically when it comes to photoelectric, right? This effect can be described by the equation E is equal to H, F is nothing but the frequency over here, minus phi. Okay, here E is the kinetic energy. Okay, this is the kinetic energy. H is the Planck's constant. F is the frequency of incident light. It is nothing but frequency of incident light. Okay, and phi is the work function of the material. We know that, right? So kinetic energy of the emitted photoelectrons is directly proportional to the frequency of the incident light. We can tell that. So there are like a few terms related to photoelectric effect that we can like that we have to keep in mind. Okay. So few of them are threshold frequency. Okay. Firstly, we'll talk about threshold frequency. Okay, so when we talk about threshold frequency, it is the minimum frequency of light. It is the minimum, okay? It has to be remembered. It's not the maximum, but is the minimum frequency of light required to cause the ejection of electrons from a material. Below this frequency, no photoelectrons are emitted regardless of the intensity of the incident light. Even if the intensity is very high, okay? Intensity is very high. It doesn't matter because it in the end depends on the threshold frequency. If there is a light coming with a frequency, let's say F, which is less than threshold frequency, F naught, then there is no emission that takes place, no emission. Okay. This is one thing that we have to remember. And what are photoelectrons? Photoelectrons are nothing but the electrons emitted from a material due to photoelectric effect. Okay. These electrons are indistinguishable from other electrons and are distinguished because they have been ejected from an incident light. Okay. And what is the work function? So the work function is basically, we'll talk about the work function now, right? So what is the work function? So work function is basically the minimum amount of energy required to remove an electron from the surface of a material. Okay, it is crucial parameter since it determines the minimum photon energy required, right? So this is again the minimum amount of energy, right? Yeah. And next we'll talk about the stopping potential. What is the stopping potential? Okay, the stopping potential is nothing but the potential difference at which the photocurrent stops flowing in the photoelectric setup, right? So it is the potential difference basically, VD, let's call it VD, such that the photoelectric flow is there, right? The current, it stops, okay? This potential difference is directly proportional to the frequency of the incident light. It is directly proportional to the frequency of incident light, okay? And the process of stopping photocurrent is instantaneous. Okay, it's not this, it is instantaneous. A new thing to remember. Right? Okay. Moving on to the next part. So, what are the laws of photoelectric effect? So, the laws governing are, the first law of photoelectric effect is nothing but it is the direct proportionality between the intensity of electromagnetic radiation induced by the photoelectric radiation. Okay. So basically, what we're telling is the intensity doesn't really matter much. It always depends on the threshold frequency and everything, right? Okay. So we know this. Now let's talk about one of the theoretical questions that we could get. And those are basically mostly on the topic of Davidson and Germer experiment. Okay. So we'll talk about a little about Davidson and Germer experiment. Okay, this is one of the topics that you have to go through. Okay, so what did they do is the experiment included a few steps. Okay, a beam of electron was produced and directed at a crystalline nickel target. Okay, the target was crystalline nickel. Okay, so a beam of electrons were targeted over there. Okay, the atoms of the nickel crystal scattered the electrons, and the angular dependence of the scattered electron intensity was measured. So they saw that the electrons scattered, and also the angular dependence and everything was measured. The electron beam was moved on a circular scale, and the intensity of the scattered electron was measured at different angles. By changing the accelerating potential difference, the accelerated voltage also varied from 44 to 68. So what were the observation made was the electrons exhibited wave-like behavior. Okay. And then it confirmed the de Broglie hypothesis. So this confirmed the de Broglie hypothesis. So therefore, this experiment was deemed to be very important. Okay. So with this, we covered a lot of topics today. Firstly, we started with the questions, and the questions were mostly based on the de Broglie wavelength and the Einstein photoelectric equation, right? So, but then there were a few things to remember. There were questions wherein the threshold frequency or the threshold wavelength wasn't met, and therefore we had to like decide if there was this photoelectric emission that happened or not. There were questions on work function. There were questions wherein we found out the de Broglie wavelength. And there were also questions wherein there was this theoretical questions about the cathode rays, ionization, and everything. So, and then later on, we discussed a few important concepts, what the definitions mean, and everything. And we also discussed the Davidson-Germer experiment, from where you might get theoretical questions like what was the target and what exactly did it prove and everything. Okay. And there's another one that you can go and check out, Arthur Compton's experiment too. So that also established the wave particle duality hypothesis. So basically, all in all, dual nature chapter is all about the particle behavior and the wave behavior of the same matter. Okay. So this is the whole concept. Now, what is your responsibility to do is to go back, try the questions on your own, and if you find some difficulties, come back and check the answers. How do you solve it and everything? But you're not going to limit yourself to those questions only. So, if in case you come across a question wherein you just are calculating, let's say the stopping potential, then go further and calculate the kinetic energy or the de Broglie wavelength or any such things. Okay, so it's like don't limit yourself to that question only. The more you explore, the more perfect you get in these questions. And also, this chapter has, you could get more questions on theory part. Also, we faced a few questions in the theory part today, and there would be other questions on the experiments that I mentioned right now. So please go through those too. And finally, I would like to say the actual pro tip for always is going to be check the units. Most of the time, they're going to confuse us with the units and everything. So, our responsibility is not to calculate the right answer, but not in the right units. So that thing should be on the back of your mind, so that it shouldn't be like you just get the answer, but then you just mark the wrong answer, right? So these are a few things that you have to keep in mind when you're doing it. And I hope you like this session. Thank you so much.